So let's see, fully half the class, basically 60% say it's false. The missense mutation is more likely to have a negative effect on a protein than a nonsense mutation. 40%-ish say it's true. So I'd love to engage in a little discussion about this point. If you said it's true, why? And if you said it's false, why? Because it's not necessarily a true-false thing. There's some gray area in here to discuss.
I said false because a missense mutation will code for a completely different protein, whereas a nonsense mutation, it'll just skip over that that amino acid and just kind of go on with the rest of it.
Okay, so missense incorporates a new amino acid. What does a nonsense mutation do? It inserts a stop codon. So a missense mutation will turn one amino acid into another amino acid, changes the amino acid, but a nonsense mutation will introduce a stop codon. So which one of those is worse? Is it worse to have a stop codon put in where there wasn't one before, or is it worse just to have one amino acid change to a different amino acid? It depends on the circumstance, but in general, having a premature termination codon, a stop codon early, is probably worse. So if you imagine a messenger RNA that has a stop codon normally here, somewhere towards the 3' end of the messenger RNA molecule, and let's say the AUG is there, you get a protein produced of a certain length. Let's say that's 20 codons worth of sequence. What happens if there's a nonsense mutation halfway through the complementary or the coding DNA sequence? So let's take the same messenger RNA molecule. It's got the same start codon, but it now has, it's still got its original stop codon, but now it has a new one. That's the nonsense mutation. How long is the protein going to be? It's going to be from the start codon to an in-frame. This has to be an in-frame stop codon. And that, by definition, is what a nonsense mutation means. It means it creates an in-frame stop codon. So now you've got a short protein. It's still debatable, though, because that one missense mutation changes one amino acid to another amino acid might have as severe an impact on a protein as what this would produce, which is what we call a truncated protein, a short protein. The N-terminal amino acids are the same, but then there's a stop codon, and the rest of this CDS doesn't get translated because translation stops right there. So either answer is fine, but it seems more likely that it is true more often truncations of proteins are worse than having one amino acid replacement. Indel versus point mutation. Which one's worse? You said indel true, and indel is likely worse. So if you said true in this, what was your reasoning for saying that? What is a property of an indel mutation that's different than a point mutation?
It takes out or puts in chunks of material that wasn't there before.
It puts out or takes in chunks of material that wasn't there before. The key word there is chunks. Right? A point mutation means you're altering a single nucleotide. An indel could be an insertion of a single nucleotide or a deletion of a single nucleotide, or could be an insertion or deletion of lots of nucleotides. And so depending on the number of nucleotides that are involved, that might have a bigger effect on the protein that's encoded. So you can imagine an insertion of 20 nucleotides could be have a much more drastic effect on the protein than a point mutation. But can you think of a circumstance where that wouldn't be true? where a point mutation would have a bigger impact than a small indel, let's say. When can one mutation have a really big difference on the protein?
What happened in the start codon?
Good example, if a mutation changed the start codon, then you might not get any translation at all. Big effect.
Yeah, or changing it to an end codon.
Or a, what's that again? Missense or nonsense mutation. You create a stop codon.
Nonsense.
Nonsense mutation, right? Single point mutation could have a huge effect. So these are just sort of general questions to help stimulate a little bit of discussion about the different types of mutations. Again, there are no real true or, this is not real true or false. There's a lot of gray area and it's open for interpretation. It depends on the specifics of the mutation of what it does to the protein. So thanks for doing that. Thanks for your student ratings. If you didn't do the student ratings, you walked in after we started, please do them online. There's a button on Canvas for doing that. All online ratings of instruction this term. So we'll finish up translation this class or next class. See what happens. Get to that. Let me load in a few of the examples of work that you did while you were waiting for this process to finish. So write a coding sequence that encodes the polypeptide, whatever that is, mRWC, and then a nonsense mutation, so trying to create a stop codon. So what's the difference here? What kind of a mutation is this? It's a nonsense mutation, yes, but color coding indicates that there's an A there. How does it compare to the original sequence? Is this a point mutation or an indel, in other words? Well, let's see, if we align GAU, right. So it seems like it's a point mutation from G to A. What does that do? Does this actually create a stop codon?
No.
So we've got reading encodons, AUG, CGA, stop codon, UAG. Where there wasn't one before, because what was the codon before this point mutation happened? In the original, it was UGG. So that's M, R, UGG is tryptophan. So that single point mutation in the second position of the codon changes UGG to UAG, creates a stop codon. It's a nonsense mutation. So good job, whoever it was that came up with this example. So an example of a SNP, another example of a SNP, a point mutation creating a. Let's look at least one other one. So, spot the mutation.
UAG. It's from UGG to UAG.
Was that the same one we just saw? Looking at codons, so there's a G to A mutation that creates, that's the same mutation, isn't it? Is this the only way to create a stop codon starting with the original CDS there? What's something else we could do to that top sequence that would create a premature termination codon, aside from this mutation?
An A2U in the second codon.
An A to U, so let's see, second codon, this first A. So you could create A to U, that would create a UGA, which is a stop codon. Is there a way to use an indel to create a stop codon, an insertion or a deletion?
Delete the first A.
Okay, so yeah, that's a good one. So what happens if we delete the first A? Then the first codon is?
UGA.
Okay, so now let's talk technical details. If there's no start codon, then translation never started. So is that a stop codon? And are we all really here, or is it just a figment of our imagination? But yeah, so that does create a stop codon. I think at least you get the point, that an indel could also create nonsense mutation. So it's not just point mutations, indels, insertions and deletions of the appropriate type can create stop codons. So thank you for participating in that as well. Good job practicing. Oh, but codon. Understanding the effects of mutations on proteins. I guess we'll continue on in that respect as well. So this is one of the exercises that I had asked everybody to work on for today. Just to explore the effects of these types of mutations on amino acids as well. So so this is the original protein sequence. Start codon, and then reading through codons, you get how many amino acids is that? 7 amino acids? What is this still? Oh, this was MPLEASE. M, please. So that's the original protein sequence. Everybody remember that? Because we're going to see how these mutations affect that sequence. So what happens with this synonymous mutation? Here. So this A is the red A is the new mutation. So it's a print mutation. It used to be a C, now it's an A. How does that affect the protein sequence? Or does it affect the protein sequence? CUC, that codon encodes leucine, so does CUA. And so what is this? What is the concept that's reinforced by this type of mutation? Which position in the codon is it, and what's its effect? Mutations, right, in the third position, the last mutation in the codon, and it turns out that in this codon, anything that starts with CU encodes leucine, so it doesn't matter what the nucleotide is in the third position of the codon. It's a synonymous mutation. DNA sequence changes, yes. Amino acid sequence changes, no. And remember, at the end of this, hopefully you've worked on this, and please give me feedback if you have. At the end of this, we're going to try to rank all of these different types of mutations and the relative effects, the severity of the effects they have on the protein that's encoded. So in general, is this a severe mutation or a mild mutation? Mild. On that scale, hopefully you're saying mild. It didn't actually even change the amino acid sequence of the protein. So here's an example of a non-synonymous mutation. So again, that red nucleotide is the one that changed. So GAG becomes GAU, changes, yep, GAG, yeah, glutamic acid to ASP, aspartic acid. So slight change. One amino acid changes. Mild effect or major effect on the protein? I don't know. Depends. And then we could go into biochemistry class and discuss the difference between glutamic acid and aspartic acid. They're both acids. They're both about the same size amino acids, but this is not biochemistry, so we won't go there. But if it's important for that protein to have a charged amino acid at that location, maybe this is a mild effect, but if it was glutamine to or glutamic acid to tryptophan, it could be a big effect. So that's open for interpretation. Nonsense mutation. If you describe just in words, what's the overall effect on this protein by the introduction of a premature stop codon with a single mutation like the ones we just created? G to U turns a glutamic acid codon into a stop codon. What's the overall effect on the original protein sequence?
It just loses
in this case, yeah, it's shorter by a single codon. It depends on where the stop codon occurs in the protein. Right? If this mutation had been somewhere else, it could have had a much bigger effect by truncating the protein much earlier in its sequence. So this one may be mild. Lose one amino acid at the C-terminus of the protein. So if we delete the final C of that serine codon in the original sequence, what's the effect? What happens to the protein? This is one of those examples we talked about, or at least I quizzed you on, surveyed you on, before we went on break. Does a deletion necessarily mean that the protein is going to become shorter?
No,
In this case, what happens to the amino acid sequence?
there's no stop codon, so it just goes on until, who knows?
Who knows? At least we don't know because I terminated this example here, but the deletion of that third position C means that the reading frame shifts. So to UCG, and then AAU, AAG, AAC, we just keep going until we find the next stop codon, but there isn't one in this sequence. So the ribosome just keeps translating because it hasn't hit the stop codon yet. This one nucleotide mutation changes the reading frame. So one nucleotide deletion get an insertion of who knows how many amino acids. These are not amino acids, of course, that are normally encoded by this gene. So now you're basically making a protein that's got a bunch of random amino acids at its C-terminus. Who knows what that protein would do? That's not what was intended by the sequence of the gene. Any questions? Just kind of trying to go over some of the prime examples, just individual examples of some of the patterns that deletions and effects deletions can have.
How often do mistakes happen in RNA processing? Do you happen to know?
I don't know in general. It depends on what you mean. Don't you love this? It depends on what you mean by mistake. Right? So alternative splicing you could consider to be a type of mistake, which happens all the time. You know, how a protein decides which introns to take out, whether or not it takes out some of the exons along with some of the introns. Maybe it's a planned mistake.
And I guess maybe how often does it have detrimental, like fatal
Right.
problems?
Yeah. And then we saw one example, so I don't know in general. I don't know if anybody really knows in general. We did see an example of that last Friday. I think it was last Friday, last Wednesday, we were talking about the breast cancer mutation case study reading, where they did find one mutation that changed the way the gene spliced. And that was associated with an increase in the probability of getting breast cancer. Don't quote me on this, but my guess is that there are way more ways to screw up transcription and translation by mutation than there are to improve things. Is that maybe a fair thing to say? Genes are very fragile. Right? A single gene encodes a single gene encodes multiple transcripts if there's alternative splicing, but the proteins they produce exist because of natural selection. So go to evolution class and we'll talk about how your genome came to be and why it is the way it is and why you have the DNA sequences you do. Most mutations are thought to be deleterious, harmful. But then there are the occasional ones that are beneficial.
Thank you.
Yeah. I do my best with what I've got. Okay, insertion and frame shift. So if you insert one uracil, that actually creates, as we saw in what you did at the start of class, creates a stop codon, a premature termination codon, so you get a short protein. The reason that we're working through this is not only to understand the effects of mutations on proteins, but because I will probably be asking you at some point to do something like this exercise, especially like what we did at the start of class on Google Classroom, design a gene sequence, or at least a coding DNA sequence, codons that encode a certain amino acid sequence, and then design a mutation to do something. Design a mutation to change splicing, to create a premature termination codon, to remove a termination codon, a stop codon. Those sorts of questions might show up on the final. For those of you that decide to take the final. And I think this is the last one, 3 nucleotide deletion. Why is the number 3 important?
Because that's a whole codon.
It's an entire codon, so it just deletes one amino acid. Major effect, minor effect. Depends on the role of that amino acid in the protein, but it's just one amino acid. So maybe a relatively minor effect. So in sum, I think we decided which one of these had the least major effect, the most minor effect, which type of mutation? Synonymous, we'll say that's the most minor type of mutation, that is, has the least effect on the function of the protein. Usually none, because the amino acid sequence doesn't change. What would come next? There were a bunch of them that didn't change, that only affected a single amino acid. And that was the non-synonymous missense mutation, which we'll say is second. The nonsense mutation also only, in this case, not in all cases, but in this case only removed or affected a single amino acid. And the deletion without frame shift, in this case again, was a deletion of a single amino acid. So those might all be tied, second most severe effects. And then it's up to you to decide how you would want to rank, if you ranked them, the deletion with frame shift or the insertion with frame shift. One of them made a much shorter protein, one of them made a much longer protein.
When it made it longer compared to when it made the insertion made it shorter.
Yeah.
I think it was much longer than it was because it only took out one amino acid with the insertion, didn't it? Or 2?
Yeah, I think so. Shorter by 1. I think it was 1 amino acid. Okay, so that would be a reasonable argument. The number of amino acids that are affected by the mutation may be the easiest way, without other information, to rank the severity of the mutations. So that would make that rank 3 and rank 4. Any questions or concerns about any of this? Here's an example of an answer to 14.2. If you want me to check yours, if you worked on this exercise, please send it to me, and I'm happy to give you feedback on it. This is just a CDS I created, 5 amino acids, MySeq. I didn't want to use tyrosine Y for a reason, so I used I instead. So I created 2 different introns. I inserted an intron between the second and the third positions of the isoleucine codon. That's that version. And where did I put the other one? Between serine and glutamine. So if there was an intron there in red, do the positions of the introns affect the protein? Does it matter if we put an intron within a codon or in between codons? When this gets spliced out, what happens to translation in either of those 2 scenarios? So what's the reading frame in this middle one? It goes AUG, AU, and then there's an intron. So what's the third nucleotide in that codon? It's whatever the third nucleotide in the AU codon. So AU, this intron gets removed. So in the processed messenger RNA, the third nucleotide in that codon is whatever immediately follows the splice site, which is another U, AUU, which is the same as the reading frame in this top sequence, it's an AUU. So by putting an intron there within a codon, once that intron gets taken out, the exons get spliced together, the reading frame is the same. And then UCA, GAA, CAA, and a stop codon. It's the exact same thing on that third example where it doesn't matter where the intron is. If the intron gets spliced out accurately, without mistakes, it doesn't matter where the intron is. Inside a codon, in between two codons, doesn't affect the coding DNA sequence. After processing is done, the messenger RNAs will look identical. And of course, this is just one of an infinite number of combinations of CDSs you could create and intron sequences you could create. If you did this exercise, is this the DNA sequence you came up with? Or RNA sequence, rather? If you did this exercise, is that the RNA sequence that you came up with that produces a protein that's have a nice day? Assuming everybody's just shy, maybe a different question's in order. Is there another DNA sequence that could produce the same protein?
Yes.
RNA sequence, DNA sequence. So how can we change this to encode the same protein? A synonymous mutation.
UAU at the end to UAC.
Okay, UAU to UAC. UAC and UAU both encode Y tyrosine. So yeah, so there are two different RNA sequences that can encode that protein. Because there are two different versions, there are two different codons that produce Y. Okay, what else? Are those the only two DNA sequences that can produce that protein?
The first three nucleotides, CAU, could be changed to CAC.
Okay, so now we're
Both of those code for histidine.
histidine, yep. So CAU could be CAC because there are two codons that produce histidine. Are those the only, well, but then there's a combination, right? Because you could have CAC or CAU at the start, and you could have UAC or UAU at the end. So that means there are four different possible DNA sequences that produce this protein. Except what?
There's a lot more.
That's only the tip of the iceberg. Because there are 4 codons that encode alanine, and 4 that encode valine, and 2 that encode glutamic acid, 4, what's N? Asparagine, I think that's 2. Isoleucine, there are 3. Cysteine, there's 2, 2, 2, 4. So how many different RNA sequences can encode that relatively simple short protein? Do you add them or do you multiply them? That's the perfect question. It's like every other combinatorial thing we've done in class. What's the probability of having an A next to an A next to an A? It's 4 times 4, 4th times a 4th times a 4th. This one, it's 2 times 4 times 4 times 2 times 4 times 2. So that's the answer to the next question in this exercise, which is how many different possible peptide sequences can encode the exact same protein sequence? I don't know, I've got the calculation up here somewhere. Did somebody do the math on it?
I got 98,304.
This sounds, sure, we'll go with that. 98,304. There are many different ways for different gene sequences to produce the exact same protein. But there are lots more ways for mutations to screw up that sequence, because most of those are only third codon position changes. That's the reason why for A, for example, there are 4 codons that encode alanine. As we've discussed, those alanine codons only vary at the 3' end. So it doesn't matter which nucleotide there, but if you mutate in either of the other two, you totally change the protein sequence. So 98,304 is actually a pretty small number compared to the total number of codon possibilities in a protein that's that long, which you could do by multiplying 4 times 4 times 4, the number of amino acids long that is. It's a huge number. So that was the answer to that question. How many different messenger RNA could produce that polypeptide? Of course, if you were really going to answer that question on an exam, you'd have to subtract that number 1 from that number, because you already produced one sequence, so the number left would be 96,324 or whatever, minus the one you already came up with. How many different messenger RNAs? Oh boy. And then there's the really hard one. If you did this, please send me your example. I would love to see it. Because I'm just trying to collect examples of how to do this. I've got one. It's on the next slides. You can look at it yourself if you want to. I'll tell you briefly what my approach was to doing this, and I'll show you my example, but I'd love to have more examples than just mine. So in general, what's the difference between these two protein sequences? So these could be two different proteins encoded by the same gene. They're just created by differential splicing. So what's the same between have a nice day and have a splice day?
SPL versus N.
Okay, so the difference is there's an N in that protein and there's an SPL in that one. The rest of the nucleotides, amino acids, are the same, which means we could have an exon, say exon 1, that encodes HAVE, histidine, alanine, valine, glutamic acid, and alanine. We could have alternative splicing that either has an exon, let's call it exon 2 for N, and exon 3 for SPL. Alternative splicing. You either get exon 1 with exon 2 or exon 1 with exon 3. And then either of those combinations would be spliced together with a 4th exon, which again has the same 6 amino acids, ICEDAY. So that's basically how I approach this question. I will not ask you to do anything this complicated on an exam, but I might ask you to do something with doing some alternative splicing of a sequence that I provide you. You don't really have enough time in 50 minutes to invent something and then proofread it, I don't think. But this is the idea. You can either splice along the top, have a nice day, ignoring exon 3, so in this case exon 3 gets spliced out with exons 1 and 2, or you can have a splice day with excision of exon 2 along with introns 1 and 2. And this is how diversity in proteins is produced, by alternative splicing. And if you really want to get into the nitty-gritty details, there's a DNA sequence that could, in theory, do that. Introns containing the 5' and 3' splice sites, and the exons encoding those codons that encode have a N SPL ICE. And then a stop codon at the end, I think. I'm pretty sure. So here's where we're heading over the next couple of days. We've only got the next couple of days left. So just one video to watch for next class. We're moving from translation into Mendelian genetics, and this is the outline for the rest of the term. We're going to work on Mendelian genetics for 2 classes. So those of you that fear the Punnett square, don't worry, it's going to be brief. Although I hope to help you make sense of it if you don't understand it already. Then we're going to do pedigree analysis, and we're going to do genetically modified organisms to round out the term. And I'm looking forward to it. I hope you are too. See you.
Google Classroom.
Oh, yeah.
But I just did it on my phone.
That's totally fine. Yep, no worries.